Let's have a few words about the execution model. What is token? Token is data structure that contains some genesis, some history of transactions, and that renders actually some current state. Current state should provide few things. One of them, proof of current ownership, like let's say public key or something, and maybe some metadata or extra data that we can use in some applications. So kind of arbitrary piece of data can be put here. If to be more exact, state actually defines the locking condition. You lock your token in such a way that in order to unlock it in verifiable way, in provable way, you have to provide some input. In very simple case, if we lock a token to a specific public key, as input we need to provide digital signature when we spend over a transaction that spends this token somewhere else. So this is very simple execution model. We go from one state to another state with a new public key and some other data maybe, or maybe empty, and so on. And for that we provide digital signature for, let's say, key 1, digital signature for key 2, and so forth. And this is transaction 1, this is transaction 2, and so forth. But this is just a beginning. In fact, our locking conditions might be much more complex and much more interesting. So for instance, we might require that, hey, in case of multisig, let's require signatures, or better say unicity proofs, for multiple keys here, like P11, P21, and so forth, PM1, where we need at least M out of N signatures, or better say unicity proofs, to unlock this state and spend the token. Why I'm talking about unicity proof and signature is the same thing. Unicity proof shows you that you are spending the given token. Okay, you're spending the given token, from the current state, let's say Pk, into the new state Pk plus 1. In this way, once we generated this proof, we cannot generate another proof that would be associated to exactly same location in hash tree, defined by the token type and the current state. With much more interesting complex conditions, we might require multiple proofs like that for each of the keys, P1, P2, and so forth. In this way, in order to unlock this token, you should provide M out of N valid unicity proofs that the given token is being spent to the new specific state. Of course, M must be greater or equal than N divided by 2 in order not to have a situation where half of token owners will provide unicity proofs for transaction moving this token to one state and another half to another state. So it should be greater, M should be greater than N divided by 2. More complex conditions could be even suggested here when we can have time locks, because we can, through unicity proof, we can also get the current time when this unicity proof has been created. So, for instance, before certain time, we spent token into one state or by one signee, let's say P1. After this time, we can spend it to by some other signee. Or it could be something else, like we can implement so-called atomic swaps, where we require that either two tokens, token 1 and token 2, change their ownership to, let's say, change both their ownerships between the counterparties, like Alice has token 1, Bob has token 2, and then at the end of this, let's say, operation, token 1 will be owned by Bob, and token 2 will be owned by Alice. Or Alice and Bob still hold their tokens. So either both swap their tokens or non-swap happens. This could also be enforced by unlocking conditions, these predicates. So let's say Alice locks her token to special predicate, we call it escrow 1, and Bob locks his token to special predicate called escrow 2, let's say. And those escrows define the conditions. Either tokens have to be reverted back to Alice and Bob, or they both only can change their owners to Alice and Bob. I will not go into much details now how it's going to be done. We are going to record future videos about this. But that's kind of just a tiny fraction of what kind of things could be implemented in a model where we lock tokens for specific predicates that defining specific unlocking conditions.